Good morning or good afternoon, depending on where you're at. Very warm welcome from unusual, very cold 65-degree Miami, Florida. Welcome to January 2020 ABC UTC webinar. My name is Atarud Azizin Amini, Director of the ABC UTC, and together with Mary Lou Rawls and Paul Lies and Jugish Kapoor, we will be conducting this webinar. The title of the webinar today is Use of ABC Techniques for the Samuel D. Champlain Bridge. And we are happy to have more than 1,200 sites that are listening to us live.
Our presentation today features the use of ABC techniques for the new Samuel de Champlain Bridge over the St. Lawrence River in Quebec, Canada. We're pleased to welcome our presenters, Guy Mailhot, Chief Engineer with Infrastructure Canada, the owner of the bridge, and Marwan Nader, Senior Vice President and Chief Engineer with T.Y. Lin International. Guy?
Yes, thank you very much. Marwan and I are both very pleased to be here with you for today's presentation titled The Use of Accelerated Bridge Construction Technique for the Samuel de Champlain Bridge. In this title slide, one can appreciate the size of the new bridge shown in the foreground. Yes, in this slide, we can appreciate the size of the new Champlain Bridge in the foreground, just downstream of the original bridge. In the background, we have the estacade and icebreaker structure built in 1967 to break the shorelines and artificial islands constructed in connection with the 1967 International World's Fair, also known as Expo 67. The original bridge opened to traffic in 1962. It was decommissioned for public use when the new bridge was fully open to traffic on Canada Day, July 1st, 2019. The design build of the new Champlain Bridge is part of a much broader project. The project includes widening and reconstructing a 1.2-mile stretch of highway on the island of Montreal with 19 overpasses, a new 1,640-foot low-level bridge linking the island of Montreal to Nuns Island, and finally, major highway works to connect the new bridge to the existing highway infrastructure along the south shore of the St. Lawrence River. This modern transportation infrastructure has been delivered within a 4.2 billion Canadian dollars public-private partnership, for which the new bridge is a key component. T.Y. Lin is the managing partner of the design joint venture. Marwan is also the engineer of record for the iconic cable-stayed bridge. If ever there was a project that could benefit from the use of accelerated bridge construction technique, this particular bridge project is certainly one of them. In fact, I can state without hesitation that in order to meet the various project objectives, ABC became a necessity. Hopefully through this webinar, you will understand why. The table on this slide breaks down the overall project agreement cost of 4.212 billion Canadian. Of interest here is the design build component of 2.245 billion, of which approximately 63% was for component one, the main bridge. The other components included the Nuns Island Bridge at about 9% and highway components for the remainder of the project, representing about 28%. Next slide. The project is located in Montreal, Quebec, Canada, which is identified on the map shown. The city of Montreal is located on the island of Montreal, itself located within St. Lawrence River. The smaller island in the caption to the left of the orange line is what we call Nuns Island. The overall layout is shown in plan and elevation view on this slide. The new Champlain Bridge measures 3.4 kilometers, about 2.1 miles from abutment to abutment. The bridge runs almost in a perfectly east to west alignment. To the left is the west abutment and landing at Nuns Island, and to the right, the east abutment in Brossard, the city located on the south shore of the St. Lawrence River. The new bridge consists of three main segments, namely the 2,044 meter or 6,706 foot west approach spans, the 529-meter or 1,735-foot cable stayed bridge segment, and the 762-meter or 2,500-foot east approach spans as shown. The fourth span of the cable stayed bridge crosses over the St. Lawrence Seaway Canal, an international shipping canal connecting the Atlantic Ocean to the Great Lakes region. The seaway operates about 9 months each year and closes when the mighty St. Lawrence River freezes over in the winter. Constraints related to the seaway's operation drove the adopted erection scheme. Marwan will describe this later in the presentation. The bridge is slightly curved in plan on each side of the cable stayed segment, essentially to enhance user experience when traveling over the bridge and also for aesthetic reasons. Next slide. Referring to this slide, the Bridge Authority of the Government of Canada, represented by Infrastructure Canada, dictated in its technical requirements that the bridge be equipped with 3 distinct highway corridors, the northbound and southbound corridors each accommodating up to 4 traffic lanes, as well as a central corridor dedicated to a light rail mass transit system. This system is currently being implemented by a separate enterprise as part of a larger 67-kilometer or 42-mile light rail transit network, which will cross over the new bridge. The new bridge is also fitted with a 3.5-meter or 11.5-foot wide multiple-use path on the northbound corridor. This makes for a very wide bridge of some 60.2 meters or 198 feet. Given the importance of the bridge, as well as the large cost to build it, and as well as the poor performance of the original bridge from a durability perspective, the authority prescribed a 125-year design life for all non-replaceable components. This includes the precast deck slabs, superstructure, and substructure. The stays for the cable stayed bridge are built to be replaceable and are prescribed to have a 65-year design life. Next slide. Let me now provide some context and background information to emphasize the importance of the bridge and the pressing need to intervene. The original and now new current bridge is one of the busiest crossings in North America. Some 50 million vehicles use it every year. The bridge also supports about 20 billion Canadian dollars in Canada-US trade each year. 3 major Quebec couriers converge onto the Samuel Champlain Bridge. The original bridge performed poorly from a durability perspective, mainly due to the use of de-icing salt, which became widespread practice in the province of Quebec when it first opened to traffic in 1962. This use of roll salt was not accounted for in the design of the original structure. To make matters worse, the original bridge was equipped with a very poor drainage system, which allowed salt-laden water to trickle down the fascia of the external girders. While the steel cantilever bridge, which is shown in the lower image to the left, performed relatively well, the approach spans consisting of pre-stressed post-tension concrete girders, a relatively new technology in North America when implemented at that time, performed poorly. Specifically, all edge girders, pier shafts, and pier caps have required costly major maintenance and repairs, especially over the past 20 years. In fact, over a 6-year period between 2011 and 2016, a sum of some 300 million Canadian dollars was required just to keep the bridge open until the new bridge was in place. This amount, among other expenses, was used to support all 100 exterior edge girders by steel trusses or other systems, as shown in the lower right corner image. Next slide. And I'll give a short historical timeline in the following slides. Construction of the original bridge began in 1958 and was opened to traffic in 1962. Images to the right of the slide show the construction of gravity-based pier foundations for approach spans using conventional construction techniques, as well as the erection equipment which was used to install the 350 pre-stressed concrete girders forming approach spans. It also shows fabrication of a simple span pre-stressed concrete girder. And finally, in the lower hand corner, erection of the cantilever truss over the Seaway Shipping Canal, which opened to navigation in 1959 while the original bridge was still being constructed over it. Unfortunately, signs of trouble began in 1986 when the first pre-stressed girder needed to be repaired. Later, from 1991 to 1992, the entire deck of the main span needed to be replaced by a steel orthotropic deck during accelerated nighttime closures, with full traffic restored the next day for morning rush hour traffic. In 2011, the Government of Canada announced that the new bridge would replace the existing bridge after it examined both bridge and tunnel options. In the summer of 2013, engineering consulting reports indicated that the old bridge was quickly approaching the end of its useful life. The reports also indicated that measures be put in place to accelerate the bridge's replacement. Next slide. In October of 2013, the bridge operator, the Jacques Cartier and Champlain Bridges Incorporated, had to close a traffic lane after the appearance of a structural crack at midspan in one of the post-tension concrete girders. In December 2013, an emergency super beam pre-purchased as an emergency response plan was installed. This was followed by the installation of an emergency modular support truss in May of 2014. This all led to the issue of a request for qualification in February of 2014, followed by an RFP in July 2014. This slide here provides a high-level timeline for the project. The key takeaways are the project was carried out by combining both an accelerated procurement approach and ABC. A short 48-month period from contract award to opening was used to undertake both design and construction under a design-build format. A fast-track approach had to be adopted whereby, for example, piles were being installed while the detailed design of the superstructure was being completed. The design needed to account for hazards such as wind, which required state-of-the-art wind studies and extensive wind tunnel testing, seismic, which consisted of performance-based design for a lifeline structure, ice, including ice on cables and significant ice forces on pier legs, vessel collision, and threat mitigation. A prescriptive requirement for aesthetics imposed by the owner was established by way of a set of definition drawings. The works had to be delivered to meet high durability requirements, including a 125-year design life, including high-performance concrete, stainless steel reinforcement, time to corrosion modeling, surface life design, and the development of durability plans. The construction had to account for 3 months of severe Montreal winters each season. All this was delivered under a P3 public-private partnership to add further to the fund. Marwan will now carry on.
Thank you, Guy. So I'll be walking through some of the salient aspects of how the accelerated bridge construction was used and how we designed for that. One of the key elements of all of this is to maximize the use of modular construction. That, coupled with post-tensioning and precast concrete, minimized the use of cast-in-place concrete. This gave a big benefit given the harsh winters in Montreal. Prefabricated steel elements was very effective, especially when we made sure that all connections in the field are using bolted connections and avoided field welding. Using these two methods, we avoided delays due to severe cold weather, as most of the major elements and fabrication of those elements was done off the critical path in contained environments. The prefabrication provides for a better quality control as well. It's needless to say that humans operate and do most of the fabrication, and in warmer weathers, we tend to be able to do a better job at performing our jobs. All of this led to an efficient construction schedule. Guy showed the general layout of this. I'm focusing here mainly on the foundations, and I want you to look at the a portion in blue at the bottom here. This is where the precast marine foundations, and that's where the St. Lawrence River Bridge is. On the left, at the shore, we have cast-in-place spread footings, and right underneath the cable stay bridge, we have cast in drill holes piles, or CIDH piles, as we refer to them. And on the east approach, a combination between cast-in-place spread footings and cast-in-place CIDH piles. The marine foundations, which in total comprise 38 of them, were all built using heavy lift foundation settings. The weight of those was about 1,000 metric tons. The way it was constructed is those footings, the actual riverbed is such that the soils underneath it are weathered rock, and few feet below that you get to competent rock. So most of these foundations are laid on footings which were cast on the site in controlled environment and later floated in using the Serens floating barges, and then brought into place and sunk down to a already dredged and prepared layout. What you see here at the bottom of the footings is the sacrificial jacks, which were used for leveling, and later on, once it's in place, it was tremmied. The tremmy concrete was used. The top portion that you see here above the footing is the stem, and once it's all lowered down, the stem sticks right above the water level of the river. All of this was done in 2 to 3 days when all the learning curve was figured out. What you see here is the pier bends. This is a view that was done in rendering, and if you go up to Montreal right now, you'll find the same view from the same spot. Guy talked about the definition drawings. It was very important in the RFP that the vision of the architecture for the city of Montreal was achieved, and it was very prescriptive in terms of defining the shape and of the bent cap, as well as the shape of the cross section of the piers. The pier itself is inclined, and there's the footing portion, which is right here, and that's the one that was sunk into place. This is the joint right above the water where precast elements were brought into place and then post-tensioned from top all the way to the bottom, through using a U PT, which is anchored at the top here where the pier cap is. The pier cap itself is made out of steel and was fabricated in Spain. Some of the salient attributes in terms of concrete characteristics on the project, we'll have one slide, we'll cover most of it, but as you can see, most of the concrete we used was 60 MPa or 70 MPa. The deck slabs of the cable stay bridge were at 70 MPa. Deck slabs on the approach structure were 60 MPa. And then the pylon used 60 MPa. The substructure, 35 MPa, unless it was necessary for strength, where we used 50 MPa. What you see here is an image that shows the precasting, which was done in Montreal. And these are the precast segments in place. All of this was done by use of match casting, so that when the segments arrive on site, they match perfectly, and the epoxy that's placed is basically what you see here at each level. Once done, the actual steel cap was brought in. It was brought in 2 pieces. Each one weighed 200 tons, and then there is a centerline field splice right here in the middle. This shows one of the V bent caps fabricated and is being lifted into place. What we're looking at here is the centerline splice, or the original design was using steel connections with anchor rods that go using stiffener plates. As we advanced the engineering and started constructing it, we realized that fabricating those elements is going to be tricky in terms of achieving the mill-to-bear requirements. So instead, we switched the design from a steel connection to a composite connection, in which we used post-tensioning and composite behavior, in which the concrete with shear studs achieved the same capacity of the connection. That was done about early on. About 10% of the connections were in steel, and then the remainder was all in concrete. This is a rendering of the cable stay bridge, or the signature bridge, which crosses the seaway. The cable stay bridge is 240 meters or 787 feet main span, and 124 meters or 407 feet back span. It's an asymmetric cable stay bridge. The stays, the harping that you see here of the stays was defined in the definition drawings, and so was most of this layout that is there. You see here the navigational channel, and you also see the non-construction zone, which was one of the major drivers that dictated how we built the cable stay bridge. The cable stay bridge does not just end at W01 and E01. It spans back all the way to W02 to E02. So there is an expansion joint right here and an expansion joint right here. The main span tower is post-tension cast-in-place footing with FEIC piles, 21 of those. The lower shafts are inclined shafts with precast concrete segments. The upper shafts are cast-in-place concrete segments. The shafts are braced with a lower crossbeam and an upper precast bow tie right there. The precast segments weighed 77 tons. The concrete cross-section is a holly concrete box girder stacked on top of each other and post-tensioned. The joints remain in compression under service load that applies to both the tower as well as the piers throughout the bridge. This shows an image of the precast, the erection of the precast elements of the tower. A total of 44 precast lower tower leg segments were needed, and up to 3 to 4 segments were erected per day, and all completed within 36 days. Air tightness tests were conducted 2 days after the epoxy was done. This was important because the durability, as Guy mentioned, was one of the key elements why the bridge was being replaced, the old bridge, and we wanted to make sure that we have the quality control that is needed between these segments. So no leak at the joint, validated with soap water. The pressure was kept at 100 psi for 5 minutes without any loss per PTI recommendations. And drilled cores later were taken out from the test specimens at 45 degrees to show that the epoxy on all surfaces were intact. Core samples were later tested for strength as well. The MFT upper shafts are 15 in total per leg, and they were all cast in place. One lift was cast every 2 weeks with jump forms. One of the key elements of the cable stay bridge is the saddle. The original contemplated design was to have a saddle design with one single stay starting in the back span and going across the pylon and coming back and anchoring it to the main span. During the value engineering, early on after we were awarded the job, we decided it is better and actually more robust to actually have a link beam design which is embedded into the shaft with shear studs with anchor heads on either side and with the stays anchored from either side. This shows a 3D integrated shop drawing, which was very important. We did this on all portions of the bridge where there was congestion or concerns with congestion so that we avoid clashes in the field when we were erecting those elements. The same models were later used to do the finite element analysis of those areas by the design engineers. There is a total of 60 stay cables. The main span has 121 strand cables and the back span has 127 strand cables. Stays are not grouted. The corrosion protection was DSI provided those stays, and galvanized wire, wax, polyethylene coating with HDPE sheathing. All of these stays were installed with damping. The damping was a twin tube hydraulic telescope damper which was anchored into the deck. It was primarily put there and tested to confirm the behavior of the stays to avoid vortex shedding, rain wind induced vibrations, galloping, as well as any excitation from bridge vehicles and any other impacts. This shows the bridge in the wind tunnel model. We tested the bridge during construction as well as the completed bridge to satisfy the wind criteria. This is an aeroelastic model that was tested. We also did a section model test of the bridge. We also performed stay testing for ice accretion Based on experiences that we've seen in North America, in the Portman Bridge specifically, ice accretion on the stays can accumulate in an icy storm, and then it can fall on traffic when the weather warms up. The RFP required to have that mitigation in place. The design-build team performed various tests in collaboration with DSI and concluded that the best way is to have a passive approach rather than an active approach, in which the helical rings, instead of being helical, we actually made them a complete ring, and we spaced them at closer intervals to make sure that any ice accretion winds up being small pieces of ice that if they do fall on traffic, they're not big blocks of ice that are damaging. On the superstructure, what you see here is a composite structure, composite stiffened box girders that are connected by shear studs to the deck, concrete precast deck. What you see is the standard cross section at the top. This applies to both the approach structure as well as the at the sections where there is no cross beams in the cable stay bridge. And what you see at the bottom is where there is a huge cross beam that connects the northbound and the southbound, by these cross beams. The stays are centered on either side of the cross beam. So if you look at it in total, the bridge is like a wing of a Boeing, which is 60 meters in width. The bridge was working harder in transverse direction than in longitudinal direction. The steel characteristics, for the most part, we used 500 MPa steel carbon steel. We also used stainless steel reinforcement, also 520 MPa. Welded wire fabric was also used. A325 galvanized bolts, for the most part, were used, both metric and imperial in some cases. The structural steel we used was both 350 as well as the high performance steel of 480 in some places where high concentrations of stresses were noted. This shows the fabrication in Spain. The superstructure were all match fabricated. Segments were all lined up, as you see, to make sure that bolted connections in the field work very well. It shows an image of the precast deck panels in Montreal. In total, we had 1,400 for the cable stay bridge, and in total, we had 10,000 in total. There were in total 2 shops working on this, and it worked out well to get all the precast panels off the critical path. It shows the precast deck panels in place. The precasting allowed for good tolerance of placement of the U rebar here that you see, so that there is interlocking for shear, and obviously you've got the shear studs in between. It worked like a charm, thanks to good quality control on tolerances by the contractor and its fabricator. The accelerated construction methods primarily used, as you've noticed, large segments, components to be erected, but most importantly, that was applied on the cable stay bridge, primarily on the main span, where a 900-ton lift span was lifted from next to the tower and lifted up and then taken lifted up to the place to connect to the already erected segment. What you see here is the superstructure erection for MS1, the first segment. On the image right here, you see still the bolted connections that are going to be placed, but you can see the very good fit up in terms of the erected segments versus the segment to be connected. What we're looking at here is MS1, a video of it showing it being erected into place. This is a 60-meter wide, 12.5 meter deep segment, or 12.5 meter long segment, 900 meters tall, lifted into place. Took a couple of days to get everything worked out. This was the first segment we wanted to do, and obviously the lifting gantry was being tested at that time to make sure everything is in order. But the lifting worked out like very well, and the major issue was to get all the webs and elements lined up with the bolts to basically fit them. But as we learned it, the cycle of the lift was brought down to 23 days per segment. This shows a quick rendering which shows the delta frame in which the segments were erected, and then the gantry was brought in to lift segment by segment. And then one mitigation measure that we did also during the erection of the bridge was to incorporate the king post solution, which is shown in red. The original design was to continue the erection from the main span tower all the way to E01 and have the construction joint be right here. To accelerate the schedule and have a mitigation plan, we actually introduced the king post to start erection from E01 towards segment 11 and 12, and by that we saved several months of the critical path. Shows the completed bridge, shows some of the analysis that we did in terms of a computer in RM to perform the analysis and geometry control. These are some of the construction site images of the king posts. This took a global team in the true sense to build this bridge and design it and get it to open to traffic earlier last year in June. We had people working around the clock. Given the time zone, we took full advantage of that. Some problems were recognized and people would work on it during the nighttime, and when you wake up in the morning, you have the solution already. Effective communication and collaboration was key to the success of this project. When you have multiple folks working on the project, especially in different places, it's very important to have continuous communication, have a platform in which all documentation is in one place, and streamlined accordingly. Accelerated bridge construction recap. Again, the design was done for accelerated bridge construction. It was to maximize the use of modular construction and to use precasting of concrete as much as possible, prefabricated steel brought into place, and field bolting to avoid delays and in order to avoid delays due to severe weather. Prefabrication provided for better quality control and efficient construction schedule. And I'll pass it on right now to Guy to take it away.
Thanks, Marwan. The Samuel Champlain Bridge is considered the gateway to Montreal. Meeting architectural vision and satisfying community expectations within the design-build PPP framework led us to adopt the use of a definition design in the RFP. From the owner's perspective, this method worked well. Heavy precast footings were successfully placed within the precision of the size of a golf ball using a floating pier installer despite strong river currents. Associated with the successful installation of the pier footings were the use of sacrificial jacks, as Marwan mentioned, which in combination with a green joint above water between precast components allowed proper alignment. This was key so that all the remaining precast and prefabricated pieces could align. The use of stainless steel rebar, the largest use to our knowledge in North America, was new to bridge industry in the province. This included specialized training and learning was required related to potential rusting of the stainless steel due to contact with other materials, contact between dissimilar metals, and bar bending, especially the loop bars in the deck. The development of special mixers were also a key in achieving a successful outcome. This included extensive use of self-consolidating concrete, ternary cement mixes to favor durability properties, and the use of fly ash. All works, of course, had to be completed under strict environmental monitoring. This posed significant challenges, particularly during aquatic excavation to rock using barge-mounted excavators. The excavation made use of turbidity curtains and had to account for winter operation. Finally, as one of the first projects in Canada to require Envision certification by the Washington-based Institute for Sustainable Infrastructure, the owner targeted a bronze award in the RFP. We are proud to note that the highest platinum level award was achieved, confirming that such requirements can be embedded within a PPP or design-build contract. Thank you for your attention.
All right. Is that the end of the presentation?
Yes, this concludes the presentation.
All right, thank you. Very interesting presentation. Excellent. So at this point, we are going to turn it to Paul Lies to moderate the question and answer period. We are getting a number of questions. Again, we are going to try to end the webinar no later than 10 to 15 minutes after the hour. Paul?
Yes, thank you, Atarid. Yes, Guy, Marwan, this was really an interesting project, and we've got a bunch of questions that have come in before the presentation, but also some afterwards, and they're still continuing to come in. But we'll start off. We had a bunch of comments about the 125-year design life, and you said that was stated in the proposal, I guess, that that's what you wanted. And is there any way you all arrived at that figure?
I can take that question. It's a good question, of course. Well, I explained at the beginning the issues with the old bridge. We certainly didn't want to have the same problem with this new Saint-Malo Champlain bridge. So we targeted a long useful life based on lessons learned from the performance of the old bridge, but also the importance of the new bridge. And there's a North American and worldwide tendency towards sustainable development, increasing the useful life of bridges. In Canada, we had the Confederation Bridge, which had a 100-year design life, but we've also looked at other important bridges in the world. And for example, the Federal Highways Administration for tunnels says that tunnels should be designed for 100 to 125-year design life, and they're now moving on to 125 to 150-year. At the beginning, we were comparing tunnel options to bridge options, so it made sense to compare them on the same service life. In terms of how we achieved the 125-year, well, we required the private partner to develop durability plans. They were also required to do time to corrosion modeling. We invoked the FIB Bulletin 34 model code for service life design. We specified high performance concrete with a low water to cementitious material ratio. The authority imposed the use of stainless steel. For fatigue issues, we increased the standard truckload. Of course, for fatigue, the bridge then had to be designed over that extended design life. Of course, all this under PPP has to be done under a holistic approach. So yes, we focused on design, but we also had to focus on the construction and the maintenance of the bridge over its useful life. Each component of the bridge.
Go on.
Yeah, I said each component of the bridge is subject to different exposure conditions, so each one was addressed specifically in taking account of industry guidelines and best practices. And we also had an independent audit of the durability plan.
Okay.
I could add to that, Paul, in that in our experience also, not just Canada, when you are investing in a mega project such as this, the 75 years that usually design life of AASHTO is not necessarily what people are following, and our experience is that it's anywhere between 100 to even 150-year design life. And the logic behind it stems from basically an initial investment that the owner is putting in, and that what we're finding is with very little attention to details to avoid fatigue, attention to details to address drainage, attention to some investment in terms of better quality concrete, or like Guy mentioned, stainless steel, you wind up being able to extend the design life of your bridge from 75 to 125. Obviously, the governing loads for earthquake, wind need to also be taken into consideration because the probability of occurrences change. You'd have to account for that as well. But all in all, our experience is that when you're doing a major mega investment on a project such as this, designs are in the order of 125, and it's becoming almost industry standard.
Okay, that's real good. You've covered most of that. A lot of that stuff y'all prescribed, I guess, and told them that in the things up front, and then the design followed suit. So that was real good. Here's another question that came in beforehand. The construction design was highly governed by the request for proposal restrictions. Being a design build project, would you eliminate these requirements or any of them at all?
Yeah, I could take this one. I would say that there were few requirements like the one that we just talked about, where it dealt with the durability, and that made a lot of sense. And it was something that was very much needed to make sure that all the what the final product is matches the requirement of the 125 that you see. The one requirement that was also added was obviously when it came to the aesthetics, and the aesthetics portion of it was something that was dear to the heart of the people in Montreal, and they wanted to see a bridge that looks like the one that they wanted, they saw in the renderings, and therefore the definition drawings, as you call it, were there. This was a little bit unusual on this project, not done in this amount of detail prescription when it comes to, for example, the cross section. It was dictated exactly as to what the width and the size of it, the angles, the corners was dictated. The W pier cap of the pier vents were there, where all of those were driven by the aesthetics portion of it. It is my opinion as an engineer that probably one could have looked at a different type of prescription, less restrictive, and probably achieve the same aesthetic objective and probably save dollars in the process. But that's the engineer in me. Obviously, a bridge is much more than engineering. It's an aesthetic piece of art. It's a monument to the city, and a lot of people look at it from different, and the users use it. So obviously, it's a holistic. It looks at it from a different perspective.
Marwan, I'll just add one word on that. When the government announced the bridge, the community expectations, we had renderings and the minister at the time said to the population, showed a rendering of the bridge, what you see is what you get. Okay, so there was a commitment to the community. This is what we're promising. In the end, this is what you'll get. In terms of some of the prescriptive elements other than the aesthetics, there's also always that balance to be achieved. Some would say we were too prescriptive. Others would say we weren't prescriptive enough, and we even went through an audit of the project by the Auditor General of Canada, and we were debating at what point do we let the experts and the industry deliver something, and to what extent we prescribe things. And there's different debate on that. Working with some design builders, they say if the owner knows what he wants, well, state it, and then so we don't have to fight that out later by trying to say, well, that's not what I wanted. So I guess there's two sides to that coin.
Okay. We're concentrating on design questions right now, and we'll ask, first of all, what type of hydraulic modeling was used for the structure, and were there any concerns with scour potential around the piers?
Yes, actually, three-dimensional hydraulic modeling was done for the river basin, and then that was used to do two things. One is to establish the current loading that we would see. Obviously, we have ice sheets that are there, and we were very interested in seeing how that will also, what it would do to the loading on the piers. But as it relates to the scour, the river is running at a very, the current is fast, and the scour, the weather drop was basically a concern. Most of it was, as I mentioned earlier, was about a few feet deep, and we killed two birds with one stone. We decided we might as well get to competent rock, get the foundation set on that. It gave us the compressive strength that we want, and we didn't have to worry about the scour of the weather drop.
Okay. Can you give some background about the lateral loading requirements for the piers and pylons and associated design challenges?
Yes, so the pier, obviously, the loads, the lateral loads that one would look at is the seismic, wind, ship collision. You have the current loads as well as ice loading. And in particular, just in terms of a sense, the marine foundations, or the foundations in the piers, the marine foundations were governed by the ship collision the design of those, and then in some cases thermal. Anybody that lives in Montreal can tell you, in summer it's very warm and in winter it's very cold. So thermal govern the design, sometimes in longitudinal direction for the fixed piers on the approach structure. And on most of the other foundations, especially on the cable stay bridge, wind governed the foundations and substructure design.
Okay. Let's look at a few comments on the cable stay bridge. First of all, what software programs were used for the design?
So we used primarily RM for the design. We also used Sophistique for the independent design check. We also used LARSA for the approach, and we used CSI Bridge for the independent check of the approach, as well as some local finite element analysis. We also used ADINA for the seismic time history analysis.
Okay. In the cable stay bridge, let's look at, I guess, slide 23. No, that's not right. Let me see. Yeah, slide 23. The question was, it came in the bow tie section. Was it precast? I think you mentioned that it was. Now the question was it cast in place? I think you mentioned it was precast, didn't you?
Correct. The bow tie is precast. It was cast on site. The question is very good, and I'll tell you, we've designed this bow tie in every single material you can think of. We started by cast in place. We changed it to steel, all steel, structural steel. Then we changed it to composite. Then we changed it to precast. And then the precast was the one that showed to be the most effective. It is a very complicated piece of work, as you can see. And the precasting was done in three pieces that were ultimately done, and then it was all lifted onto place.
Okay. This question came in during the talk beforehand. Was the bridge modeled to be tested in a wind tunnel? I think on slide 32, you showed that, and I didn't know if you wanted to comment any more on that.
Well, yes, I can provide a little more background. The testing was done at Boundary Layer Wind Tunnel Test in Canada. Dr. Peter King was involved in that. As you can see, the existing bridge was also modeled. The aeroelastic model, as I mentioned in the talk, was done for a couple of construction load conditions, which were deemed to be critical when the main span is halfway built. And then just before closure, it was tested. And those were conditions that were important to define the loading that we would take into consideration in the stays and in the deck. It didn't govern the design of the deck, but it got very close to it. And then obviously we tested for flutter instability, which is a requirement these days and standard. And from that, we got the buffeting loads to take on to apply to our wind load condition cases.
Okay.
Marwan, I think I can just add to that. I think that we specified what were the industry best practices in terms of wind analysis and wind requirements for the cable stay bridge portion. And I think we mentioned that the wind, it's a 1 in 10,000 year wind for aeroelastic stability. So I think we had a good coverage on the wind requirements for that project.
Okay. What were the seismic design criteria required during the design of the main bridge?
I can take that, Marwan. The owner because of the importance of the bridge, the owner specified it to be a lifeline bridge. At the time when we were preparing our RFP, the Canadian code was being revamped, but it wasn't out yet. So we talked to Dennis Mitchell of McGill University, and we got an advanced version of the new code, which effectively we embedded into our RFP. So we required performance-based design. We required nonlinear time history analysis. The TY-Lin essentially went with an essentially elastic design, and we think we had, again, best practices requirement for seismic design. There was also independent peer review requirements by seismic specialists. So again, seismic was taken of high consideration, and that was fed into the design team, which developed it further.
Okay. Was there any stage post-tensioning on the stayed cables during and after construction?
During construction, of course, the stays were stressed in multiple stages as the segments were erected in the main span, and accordingly, the back span to balance the moment in the pier were also stressed so that you don't have, if you will, unbalanced loading on the pylon. But as you kept on going and you added more and more loads, there was a fine-tuning step, which was done as we are getting close to the closure segment. And we did it quite effectively to make sure that it's not on the critical path. So usually the standard is you do most of your last stage stay stressing after closure. And what we were able to do was probably about 80% of the last stay tuning was done prior to closure. And then only 20% of the stays was done after closure to avoid having that particular step be on the critical path. But to give the audience a sense, in some of the stays, we had up to 7 steps of stressing as we went in. It was a very fine-tuned machine so that we can achieve no overstress of the stays and no overstress of the girders.
Okay, let's look at slide 22 real quick on the cable stay bridge. Yes, the question came up, was there uplift at the WO1 bearing?
No, there was no uplift for the service load conditions. There was uplift for the ULS conditions like seismic and or very, very high winds. But for the SLS conditions and the dead load, there was enough counterweight in the back span that we put here. So this was all composite. And then the main span had had only the deck panels on it for concrete. The back span had counterweight in the back span to balance the equilibrium of the cable stay, and that was also done so that we have no uplift on W01.
Okay. You want to comment on the reasoning behind the asymmetric cable stayed span configuration?
This was dictated. Yeah, this was dictated in definition drawings, and Guy can walk us through that.
That was part of the architectural vision. There was a bit of, discussions, of course, of why not make it symmetrical, but that was the architects wanted in certain that we give focus on the main span, and it was part of the architectural vision. So.
Okay. Let's look at construction. There was a question that came in beforehand. Let's see. Let's say, what were some difficulties that were encountered in the construction of the foundation? How were they addressed or overcome?
So one thing that comes to mind, I would say for the most part, is the current of the river the river is a pretty fast river, and erecting those marine, I'll go to it here. As you can imagine, as you're lowering this heavy segment, heavy foundation, which weighs about 1,000 tons, and as you're putting it in there, and divers are going down to put the floating sealer around it so that you can grout the tremie and make sure that the whole thing is right in the right location, the current was an issue. So one of the things that we had to do was install shields in sheet piling of forms so that it allows for a working place where the current is not very fast. That was an issue. Obviously, we knew about the cold conditions, but as you can imagine, in winter, working in there with the ice shelf being there made it very difficult, and we had to always go in with a contractor and break the ice shelves and make sure that they don't present danger to the workers and the workspace.
Okay. Could you describe some knowledge learned during construction that would have changed the initial design? You did mention the W beams where they connected together, the W caps, where you changed to a cast in place connection. Anything else?
There's a couple of them that I can point out to. So the first one is what you see here in this image, and it's pretty self-evident and apparent. The original bid that we had put in our bid design was that the upper portion, which is this W pier cap, as you see it here, this was originally bid as concrete. And it was a continuation of the whole concept of precasting. The idea is to precast this segment here and bring it into place, and precast this segment here and bring it into place. The weight came out to be prohibitive, 500 tons or so, very difficult to erect into place. So we changed this from concrete to steel. And this was done live after we were awarded the job. We actually turned around with the contractor, worked very quickly to design this and change it from concrete to steel. As I mentioned later, as we advanced the engineering of this precast steel element, this steel connection right here, we found that the fabrication of it was going to require mill-to-bear requirements, which is required by code for the anchor rods right there. And that in itself presented a delay in fabrication. So to avoid that, we switched from steel to concrete composite, and that presented a very good advantage and took the fabrication of the steel element from being fabrication on the critical path. We moved it away, and we're able to ship them from Spain without having to fabricate all that stiffening element. One of the elements that we did not do, and we will never know if it would be advantageous or not, is the backspan of the cable stay bridge. We contemplated it, we discussed it with the contractor multiple times, and when we built this thing, it was not easy. The backspan was built all on false work, and it was built with the steel composite elements first, erected, and then you had to put the counterweight later, and you had to erect the deck panels. It was more challenging than what we'd initially see. When we were bidding the job, we contemplated a lot if the backspan should be all concrete instead of composite, because naturally it'll be a concrete element and you can just basically erect it as concrete on false work and then have the main span be composite. That's something that remains to be something that one would never know the answer to, but it's something that always I think about.
Marwan, I could also add that you did look at the possibility even of erecting it on the ground and lifting it in place with one temporary bench instead of constructing it.
Thank you for reminding me, Guy. So the original bid was to have the steel segments be basically brought. By the way, all this area shows water, but it was all filled during construction. So it was actually land here, all of that. So in this area, it was basically contemplated to erect two false works, and based on that, do very heavy lift with everything in there. But that was also contemplated to be very difficult, and we switched to the stick building that ultimately was used to erect the backspan.
Okay. We're about running out of time. We'll try and get some real quick ones. The specifications for the precast concrete, was the fabricator supplier supposed to be pre-qualified?
Yes, there were. There were requirements to have precasters have a certified precasting plant and certified precasters. So In fact, we even went into their plants and checked their certifications and stuff. So yes, they were certified. I want to also add that they were temporary precast plants. Those as well had to be certified under a certification program.
Okay. Was UHPC used in the deck joints at all?
No. No, we kept high performance concrete essentially with the same properties as the parent concrete or the panels. And we did have the stainless steel rebar there, so that was for us it was adequate. Okay. We didn't prevent the use of ultra high performance concrete, but the bidder chose conventional high performance concrete.
Okay, and there was no overlay installed on the deck, was there?
Yes, there is. There's a waterproofing membrane and an asphalt overlay. In fact, the asphalt overlay is a bit thicker than the typical what we use in Quebec here. So we can eventually mill down the pavement and keep the waterproofing membrane. And it also allows for a bit more flexibility and adjusting for differences in elevations between the panels. So the thicker thickness was helpful in our case.
Okay, that's about all the time we have. I'm going to ask Jugash if we've got another question or two that we want to pick up on. Jugash?
Yes, thank you, Paul. There's a few questions that came in, and I'm going to try to address as many as I can. Number one, would designing the entire structure straight instead of curved would have saved a significant amount of money?
I'm not sure I follow. The bridge for the most part was straight. I'm not sure I follow the question.
He's referring to that the plan view.
Yeah, the cable stayed bridge is straight, okay, and there are very large radius curves on each side of the bridge. It's curved. I think the overall length of the bridge is about 5 meters difference between a straight bridge and a curved bridge. Yeah, so my understanding it didn't add a significant difference because of the large radius, but maybe Marwan, you can.
No, that goes to show you that when you have a curve of this nature, gentle like that is insignificant. The kink is taken in the connections, and you don't see it in fabrication. You don't camber for fabrication. It's really very, very minor. So okay. There was no impact
next one.
to the overall cost, if you will.
Okay, thank you. The next question is, was it not necessary to use cross ties between towers above the bow tie?
No, it was not necessary, but we definitely looked at that for both during construction to make sure that the tuning forks of the tower are actually stable and they don't vibrate too much.
I could add to that. It's we designed it to the 1 in 10,000 year wind. As we start cranking up the wind even higher, well, there is some vibration that starts at the top of the tower. So that's a very good question, and but it was looked at quite carefully.
Okay, thank you. What material was used between precast deck panels?
High performance concrete, much similar to what was used for the high performance concrete in the panel. So the compatibility of material there.
If you're asking about, if the question is asking about the material itself between the precast panels, for example, of the segments of the MST or the pier caps, it was epoxy. If the question is about the stitch cast in place of the concrete, which shows a big gap, that was like Guy mentioned, it was the same properties as the parent material in the precast panels.
Yeah, this was about, the question was pertaining to the deck panels, precast deck panels.
Yeah, so it's
material used for those.
It's the same material, concrete material as the precast element.
Okay. Next question was, you mentioned the critical path a few times in your presentation. What were the items on the critical path?
So it started with the foundations. And then after that, it was very clear that it was the pier caps, and it stayed being the pier caps for the longest time, the steel pier caps. And then after that, it became a race between the finishing the deck panels or finishing on the approach structure and finishing the cable stay bridge. And it was neck and neck for a while. And then at the end, the cable stay bridge became maybe about a month or two or more on the critical path. And that's why you saw the mitigation method with the king post solution, which moved the closure from segment 15 to 11, so that we bring back the cable stay back to as much as possible close to the approach. And that's how we were able to succeed to open the bridge.
And I can just add that
Okay.
they were, as I mentioned before, they were actually starting to put in the piles for the cable stay bridge for the main span tower almost as soon as they got out of the block. In fact, in the RFP period, we required that they advance some of the foundations because we were really rushing against time for, even in the design phase, of course, to get, the bridge in service as quickly as possible.
Okay. Can you tell us the longitudinal reinforcement ratio in the towers?
I don't have that on the top of my head, but it was between 2 to 3%, 2.5 probably. If you're talking about the cast in place, if you're talking about the precast panels, it was very, very small because it was just for thermal, because most of the capacity is the PT.
Right. Well, that's all the questions I had. Atarad, I'll turn it back to you. Thank you.
All right. Thank you, Yogesh. Thank you, Paul. And thank you, Marwan and Guy, for a great presentation. On that note, we will end the webinar and hope to have you back with us on February 13 for our next monthly webinar. Thank you.